Yeah. So just a quick comparison. So here we see this. Chlorine, very reactive oxidizer. Chloride, very weak reducer. Chlorine, highly unstable. Chloride, highly stable. Everybody eats chloride. In fact, they drink chloride. There's chloride in drinking water. It doesn't kill you. There's chlorine in drinking water depending on where you get your water. When I was a kid growing up, our water was sanitized using chlorine. So each time you drank a glass of water, you could taste the chlorine in the water, because they use the chlorine to kill the bacteria or any microbes in there. And so they stopped. Now they're using ozone. When they use ozone, it doesn't leave residual odor because when ozone oxidizes all the microbes in there, it forms. When ozone reacts, it forms oxygen. Well, oxygen, no big deal. It's good. And so ozonation is a huge improvement in the taste of water. Water used to not taste so great. Tap water, that is. But now it's much better, I think, in some communities. But anyway, so we see the conjugate relations. So what we say is chloride is a very poor reducing agent. It's quite stable. It's unreactive. And so in terms of HCl, HCl has H+, which is an oxidizer, and chloride, which is a reducer. It could be both, the H+ doing its oxidizing and chloride doing its reducing. But we can't assume that you're gonna react it with normal chemicals. Chloride can actually react. In fact, we generate chlorine in the lab. Because if you buy chlorine, you use storage and risk. So we only need little bits of chlorine. So if I want to generate chlorine in the lab, it's easy. How do I generate chlorine in the lab? I'll take some HCl and oxidize it. What would work to oxidize hydrochloric acid to form chlorine gas? Tell me what would work. What would work to oxidize chloride to form chlorine gas? Tell me everything you can list that would work to generate chlorine gas in the laboratory, starting with sodium chloride or hydrochloric acid or whatever, any compound that contains chloride. What would I mix it with to generate chlorine gas? Yeah, dichromate. So if I tried dichromate and chloride, would that work? Okay, now we have to it's just getting familiar with the chart. Getting familiar with the chart is this. This is the way I remember using the chart. Chloride versus chlorine. Which one's going to win for the electron? It's going to be a tie. So we need a oxidizer stronger than chlorine. Is dichromate an oxidizer stronger than chlorine or weaker than chlorine? Now we need to know our relative position in the chart. The relative position in the chart, there are two things you memorize for this chart. One, F2, 2, Li. F2 is fluorine. What's special about fluorine? Fluorine is the most powerful oxidizer in the chart. Li, what's special about Li? Well, Li solid. Li plus is the weakest. Li solid is the strongest reducer on the chart. So you have these two memorized so that you know which way's up, which way's down, because it can be inverted, like you're out in space. So you always memorize fluorine and lithium to give you your orientation, spatial orientation. So are we on the fluorine side or the lithium side? Well, we're looking for oxidizers that will oxidize chloride. And so the oxidizer's on the left. So are we on the fluorine side or the lithium side? We're on the fluorine side, which would be the left side of this chart, the right side of our classroom chart. Okay, so fluorine's the strongest oxidizer. Remember we talked about the top 5 here, oxidizers. So is dichromate a more powerful oxidizer than chlorine or a weaker oxidizer? It's a weaker. So we'd expect dichromate wouldn't work. Dichromate's not going to work to oxidize chloride. We need something more powerful. What would be more powerful? What would be more powerful than chlorine? Lead-4 oxide, but lead-4 oxide is toxic, so we probably don't want to use lead-4 oxide. Lead-4 oxide is a great oxidizer. This oxidizer is used in car batteries, so this is why this is here, lead oxide batteries. It's a great oxidizer. What else would work? Permanganate, and that's in fact what we use. We put in, we take some hydrochloric acid, and then we put in some solid potassium permanganate, which is these purple crystals here, and then you start generating a yellow-green gas. And this yellow-green gas is chlorine gas. So we take permanganate, dump it in with a chloride, oxidize the chloride to chlorine, and then we can generate chlorine gas. What else could we use? Hydrogen peroxide. Probably household hydrogen peroxide is not enough. Household hydrogen peroxide is like 3%. We have 30% hydrogen peroxide over here. You know, there's 50% hydrogen peroxide. When you get to like 30% hydrogen peroxide, it becomes kind of dangerous. In fact, there's a story. It's not a story. There's a news story that came out. There's a person who bought some hydrogen peroxide in San Diego and wanted to return to, I think, San Francisco or somewhere up, no, Sacramento. And they got a good deal on the hydrogen peroxide. They were going to use the hydrogen peroxide, I forgot for what, either for hair, for gardening, or something like that. And so what they did was, it was in like a gallon milk jug. You know, it's not the kind of container you normally put hydrogen peroxide in. You normally put it into something that's much more chemically resistant. And then they put it into an ice chest, one of those like plastic ice chests. And they wrapped it up with duct tape. And then this was security checks there. You know, and so the people doing the check-in at the airport, the person convinced them to check that as luggage. And so they checked it as luggage. It was like 50% hydrogen peroxide, I think, and it went into the luggage compartment. And then the problem was the hydrogen peroxide ate through the milk jug, and then it ate through the ice chest, and then it started dripping on some fabric luggage and caught it on fire. And so there's all this smoke coming from the luggage compartment as it was starting to burn the luggage. It's a powerful oxide. You think about it, you know, what happened to this guy? I don't know what happened, but the plane made an emergency landing and everybody survived, so it was okay. You can read about it. It's on FAA site, talking about hydrogen peroxide in this flight. But think about that. Think about it if it hit the metal. You know, the hydrogen peroxide hits the aluminum metal of the structure of the aircraft, and that could have been much worse, because metals are electron rich. Metals are powerful reducers, right? Especially aluminum, you know. And so I think that was a very lucky accident that it hit the luggage instead. You know, maybe there's some barriers. You know, in the luggage, they probably have big containers as barriers in case things leak out of the luggage or something. I'm sure they do. They've got to have some kind of, but aluminum is a very powerful reducer. That could have caused a very bad reaction. And hydrogen peroxide is much better oxidized than oxygen, you know. All right, so does that make sense? This is how we use the chart, okay, to figure things out, redox property wise.